Hi everyone, welcome to another Common Lisp Study Group. I'm your host Ron Vadum with the Atlanta Functional Programming Meetup. Today we're going to be continuing our discussion and our kind of case study of CL4th, which is the final chapter that's inside the Let Over Lambda book that we reviewed in past. Folks tuning in on the YouTube stream, please let me know if the font size is decent enough for your viewing pleasure in the chat window. So this way, if there needs to be adjustments while I'm going through some examples and stuff, I can certainly do so in real time. Last week we were off, so I'm going to do a brief review today of what we got done before we get into today's material. And then we'll just dive right in and doing some debugging of our fourth interpreter that we've built up so far with the provided methods that were given inside the book, and we'll be reviewing some of the examples, in fact, of that was provided in some of the code examples that were provided in the book, so that way you could get a better understanding of how this fourth interpreter is getting constructed up until now. In addition, time permitting, I'm hoping for us to get past some of the technical issues that we've been having with some of the examples, and hopefully get into some of the later parts of the chapter, which starts building some interesting things on top of our fourth interpreter. So last time we actually stopped kind of in a debugging session where we were having some issues with dealing with actually evaluating certain things inside of our fourth interpreter. Turns out that was more in line with how the code was structured when I was doing an eval when I was doing the last stream. I went ahead and corrected those, so now our fourth interpreter has the ability to actually push stuff onto the stack, as you can see right here. I'm going to go ahead and clean this up and start this up again, just so folks can actually see this. Let's load up our fourth. Let's go in and set our package to AFP fourth demo, and then we will go ahead and set off our fourth demo global variable that we have defined inside our main file with fourth interpreter. And then you can see that if we go in and run the following line, and we run the Pandoric macros, and recall our Pandoric macros give us the ability to reach into the new fourth closure and actually access particular member variables of the object, so we can actually inspect it in real time. We'll see that what we did is the order in which we through the variable data that we just passed into the new fourth interpreter gets stored into the stack in a LIFO manner. So the first value is obviously going to be the last value and so forth. But obviously this isn't going to, be useful. What we'd really like to be able to do is not only pass in data, but also run operations on that data. There's a couple of ways of doing this. Let me go ahead and reset this because we have some invalid values here. One way is actually the following, which is running fun call directly into our fourth interpreter. So if we go ahead and call, because recall, new fourth is a closure, so we could use fun call and apply on it. We could certainly, add, uh, an operation of 3 duplicating 3 on the stack, squaring it, so 3 times 3 and then printing it out. So this is going to just print out 3 squared. When we try running this, you should see something interesting. And this is probably going to illustrate one of our first issues that we have not yet addressed, which is dictionary lookup inside of the new fourth interpreters is not working as correctly as I originally anticipated. This is something that I noticed this morning because I thought I had this working last night, but when I restarted my Lisp REPL, it looks as though there was some confusion as to what was defined inside of the source code and how it was corrected. So we'll go ahead and correct that in real time today. But let me just go ahead and illustrate the problem. If I run this code as is, you'll see that it actually did do what I expected it to do. Weird. It must have been a problem with my previous restart. So, good news, I've actually corrected this. I will check this in and throw this into so folks can actually try this out and make sure that I'm not making any mistakes here. But let's go through this clumsy way of actually interacting with the interpreter. What you're doing effectively here is you're applying for the fourth closure to grab the argument that was passed in one at a time and interact with that value first before moving on. So you could certainly write your code this way because you're essentially interacting with the stack one at a time and essentially doing a lexical scanning yourself. That's kind of useless for folks who want to write real code because I doubt folks would want to write code with explicit fun calls, more importantly, code that doesn't clearly show the essence of the fourth code, which is this. This you could clearly look at, and if you know fourth, you can actually read that as saying that we're squaring 3. Here you have to, from line 254 and 257, you have to act like the fourth interpreter and recall what it's doing, and then eventually you'll recognize that this will do what it was originally doing, which is printing out 3 squared. Another way of doing this is obviously, and this is what we're ultimately going to get to, is run code like this, where you're passing not quoted. Notice that our operations are not actually quoted at all. This is particularly important because what you want your fourth interpreter to be able to do when you're instantiating it and even interacting with it is pass in a bunch of fourth code the way you would normally write in a text editor, and then it would actually do the right thing, which is read it in one at a time and then interact with it one at a time. So this, if we actually go ahead and run as well, you will see that it will do the same thing that we did before. But the difference is cognitively speaking, when an end user, a person who knows fourth looks at this code, knows what you're actually trying to do. You took a line of fourth and actually pass it into the interpreter, and it will just go through and scan it the way it should. Let's first go and look at what this new fourth interpreter instantiation did, and then what we'll do is we'll go and macro expand go forth to see how it's evaluating this particular example. So, okay. So if you recall our new fourth interpreter, the way we wrote it, we ended up writing it. So we used an anaphoric macro to actually go in and uh, take our list of fourth registers and create essentially a dictionary through fourth install primitives. And what that does is it will grab everything that's in the global fourth registers and then specifically the standard library that we currently have. And it will apply the actual value in the fourth standard library into the dictionary that's available inside um, the fourth register's global variable. Then what we do is we do a lookup inside the dictionary to see if the particular word in our code is available inside our dictionary that we've defined earlier in the fourth standard library. And if it is, we call fourth handle found, which will ultimately, at this point, that word that we're currently evaluating is already available on the parameter stack. Fourth handle found will have access to this parameter stack, and will go through and evaluate that particular operation or that particular code base. Fourth install primitives, again, what we did last week was nothing more than a macro that takes in a given word and creates the actual fourth word that it represents, and it separates the actual code, which is the code block. Has its thread variable. So if you recall what a thread was, what we were talking about when we were talking about const threading, thread in fourth has a very specific context, and that is it is taking the code block, and that code of execution is the thread in which a particular piece of data is flowing through, and these threads can be interwoven based on the current thread that you're actually evaluating, and that is the current code block that you're evaluating. Now, again, if you remember what we talked about last week, and this again is just part of our review today, this is based on how the immediate mode of the value is going to be worked on to determine whether or not it's going to be directly executed. That is, whether or not that current thread block is going to be directly executed, or it is going to hold off until it gets back into immediate mode in order to execute that again. And as you can see there in my comment there on line 182, immediate mode is a mode in fourth programming that deals to determine if a particular fourth code is compiled or directly executed using a flag. If it's a 0, it means that the fourth code is just going to be compiled as is. But if it's non-zero, what that tells fourth to do is the following. It is, just go and look at my notes here. Right. Oh, my apologies. So if it is 0, fourth is in what's called executing state. It will take the value and evaluate it at runtime. If it's non-zero, what happens is we are compiling. We're taking the next set of fourth words and we're combining them into making a new fourth word potentially. This is how it's often used. You create new fourth words based on some of these sets of values, and that's actually how you would define what we would consider to be like a function inside Lisp. And I'll give an example of this because we need to add 2 more primitives into our fourth library in order for us to do this. But before we do that, let's finish our review here. So let's go in and look at how our new fourth interpreter looks like now. And before that, let me just add 2 more things. In order for us to actually have our interpreter do what it was doing right now, which is evaluate and execute the code, we needed to actually implement 2 additional pieces of code, actually 3 additional pieces of code. One is related to these 2 particular functions, and that is, what should we do when a particular word is found, and what should we do when a particular word is not found? And by word is word a fourth word that we haven't defined yet in our dictionary. So I went ahead and added this into this code here. Fourth handled found, what it does is it checks to see if we're in compiling mode, and if the word that we're looking at is not in compilation state. That means we're in so we're in compiling mode, and we're not actually the given word is interpretable but not compilable. So what we would do then at that point is we would just go ahead and compile in the given threaded word into the code. So that means it's taking the thread block that represents that given word and compiles it into the word that we're trying to compose. And again, you'll see this will become clear when we start talking about some of the immediate macros and start dealing with function declaration. Otherwise, what we would do is this means that we are in interpreting state. So what we mean in interpreting state inside the fourth interpreter is we're taking the given code block that this word represents, we're passing it to the program counter, and then we go back and call our inner interpreter, which is the set of conditionals, if you recall, that will deal with whether we're pushing something onto the parameter stack, or we're actually invoking a particular function call by doing the parameter stack return stack dance. It will move around the given thread into the return stack, call the function, and then it'll move stuff from the return stack into the parameter stack and move on. So just give you kind of a brief, a quick review on how this looks like, if you recall. Give me a second here. Fourth inner interpreter. Okay. So this is what our inner interpreter was doing, if you recall. It basically checks to see if it's a function. If it's a function, it'll just go ahead and call it. Otherwise, it will just go ahead and do the dance between the return stack and the parameter stack. So let's see how this is expanded inside our new fourth interpreter. Sorry for folks for chiming in, seeing the jumping around here, but I tried to structure it as cleanly as possible. Okay, so let's see if we can expand this, what this looks like. So you can see here, do a expansion on this. Forth install a primitives basically grabs every dictionary word in the Forth standard library and adds them to the given dictionary here. There's a couple of operators here that I will explain a little later that I added to deal with some of the immediate mode stuff that we'll be covering today. But for the most part, this is pretty much what we've covered up until now. It'll create your standard library functions, and then if we go into what this does, it is just calling the particular value in the standard library to essentially set it up so that it can be invoked by our p lambda here. And what our p lambda does, if you recall, it creates this this environment that will take in the value, do the lookup, and then it will call, our macro Forth handle found if the word is found. And again, this here will compile in the given word. Otherwise, it will go ahead and evaluate it. The reason why I'm showing you this expansion is for folks who are not familiar, who haven't been this is again a review on how macro expansion works. This is kind of illustrating the power of macros. With very limited amount of code, if you define your particular code generations in a very concise and controlled way, you can actually declaratively specify how you are constructing something, and then you can let the Lisp compiler do what it was intended to do, which is actually generate the appropriate code, evaluate it the way it was intended, in some cases compile it to machine code, and so forth. You're trying to essentially delegate as much of the code generation process from a correctness standpoint, especially if you know the template on how a particular function or functional pattern is structured, to the Lisp compiler to do its job. And it will go ahead and it will take that structure that you created and leverage it wherever appropriate, making sure that it doesn't, provided that you actually follow, standard practices for using the macro system, for example, using things like gensim where appropriate, being able to use anaphoric macros where appropriate, and so forth. Are there questions about this? Okay. So let's go ahead and before we finally dig into today's thing, also do one more, which is what is happening when we then call go forth on this code. So if you noticed what it was originally, which is our forth code, what our go forth macro does effectively is take that code, creates it into a list internally here, and then it will call directly the Forth interpreter on that word. Now, this effectively is equivalent to what we did earlier, but now no more do you need to worry about doing this kind of structure and remembering the ordering of your operations. You can actually write it the way you would normally write Forth code, and it will go ahead and do its job. So today we're going to be talking about immediate modes. We're going to be talking about adding a couple more things with for functions, user-defined functions that we could do in real time, and so forth. And we will hopefully get to the Lisp stuff that writing Lisp inside Forth that was provided inside, which is part of the case study. So the first thing is immediate mode, like I was talking about earlier. Again, let me just go ahead and correct this in real time here. If it's let's flag. Let's go ahead and do this. Dang it. Stupid. My apologies. For some reason, smart parens is causing some weirdness with my interpreter, my buffer. So let me go and write this as much as I can. Okay, so like I said, immediate mode deals with compilation, whether or not we're in interpreting state or in compilation state. We need to write just two things that we need to make sure. If 0, what does this mean? This means that the interpreter is in what the book is calling right now executing state or regular interpreting state. So we're going to go ahead and use that terminology too. Regular interpreting or executing state. Now, state. Go. And if non-zero, let's just go this way. This way, we'll just keep it right. The interpreter is basically in a state where it's going to take the set of words and it will check to see if the word is an interpreted word or the word is an immediate word. If it's in this immediate, so that means if we're in immediate mode and there's a word that is an immediate word, it will go back and it'll escape out of that environment and it'll execute that, and whatever the return value of that will go and be injected into this compilation state. So this allows you to then execute, different types of Forth code at compile time. So if you switch over to this mode and try to generate stuff, it'll go ahead and it will execute that instead of evaluate. It will evaluate instead of actually generating code based off of it. You could think of it this way. You could think of this like if we're generating a macro, it allows you to execute. It's like an unquoting operation. That's kind of what I was kind of getting the sense of when I was trying some of these examples. And I think if we, as we go through this, it'll become clearer as to where this becomes particularly useful. So let's go ahead and just write that as that. Is compiled. All right. Okay. So In Forth, standard Forth, there are two primitives that deal with whether or not we are in immediate mode or not. And that is the right brace square bracket and the left square bracket will determine whether or not we're in immediate mode or not. Now, this is going to sound a little weird, and when I show you the example, it will definitely look odd. But the way we determine whether or not we're in immediate mode or not is if we end up using our left square bracket or right square bracket like this. If it's in this order, we are interpreting words in Forth, which means they'll be automatically executed in real time. But if we have it written in this way, this means that in this section here, we're compiling words in Forth. So you're going to see an example where the left bracket, the right square bracket is before the left square bracket, like this notation here on line 190. And it's going to definitely look a little jarring for folks who used to curly braces and C-like languages where the left curly brace is always before the right curly brace. But it will make sense when we start adding a couple of primitives later on that essentially abstracts this guy out. But this is the reason why some of the code examples in the book, at least, puts you in and out of Forth mode to indicate whether or not you're compiling using this notation right here on line 190, because they want interpretation mode to be the normal way of you handling the square brackets, and compilation mode to be the odd man out, so to speak. So we need to first define our immediate mode notation, and that literally is dealing with whether or not we are compiling or not. So we have a flag calling compiling flag that will deal with the actual compilation of the word. There's one more thing I wanted to actually bring up, but you know what? I don't think we got there yet. We have not got there yet. Alright, that's fine. Okay, so we have this compilation flag that's setting up our code. This here, obviously, I think I already compiled this guy in MCF, oops, there we go. Obviously, using this isn't going to be enough. We need to figure out how to actually, what does this mean? What does compiling a word mean? So, in our Lisp implementation of Forth, what we're going to be defining compilation as is we're going to take the code block of a given word that's already defined in the top of our dictionary, and we will essentially take that code block and set it to being the concatenation of whatever the current word that we're actually going and defining, and it's going to be usually a list of these words, because it might be a sub-block if you think about it, and the and itself. So that's what this is doing. We are using n concatenation, which means that this is a destructive operation. We're taking the set f and we are setting it to being nconc of the current code block that's defined by the top of the stack's word and the actual word itself. Now, this is what's ultimately used by fourth handled found, which is what we were showing I was showing earlier, and that is essentially then leveraged to um, essentially put us in execution state or in um, compilation state. So based on this compile flag, we check the current word that we're actually looking at, and that's very important. The current word, if it's an immediate word, regardless if we're in compilation state, is going to be interpreted again. That's something that's particularly important to know. Just if you're writing fourth code ever and you are dealing with immediate words versus compiled words, that's something to be aware of. And then otherwise, it'll do what we were reviewing earlier, which is going into interpretation mode. What we didn't cover earlier, but I think it's important to cover now because we're talking about immediacy, is what does this mean then if the word is not found? And that's something to be particularly cognizant of, because there are a couple of cases of checking to see if and these are special conditions almost, that you need to be aware of, so that way you can actually deal with them accordingly. What fourth handle not found deals with is the particular handling of a word that's not in the dictionary, and the way it does it is by expanding into a lexical environment that actually contains that given binding, that given word, and we will then look at it to see, based on particular cases, what we need to execute for. For example, let's say that the word is a symbol. All right. If the word is an actual symbol, which means, and by symbol we mean a Lisp symbol, we'll just throw up an error. Okay. That means we're using something that is not defined in our dictionary, and we didn't have a case of leveraging this we didn't actually have any sort of definition that was even it's based off of, and that's including things when we're getting into compilation mode and so forth. But there's two special cases on top of that. Well, one is whether or not we're using quote, which is a quoted value. In this case, when we're using quoted value and we're in compilation mode, then we're just taking whatever is available in that binding and then compiling it in. So it's kind of a no-op in that case. But if we're in execution mode, quoting something means that you're throwing it as a parameter. So even if it's a dupe, if you use dupe, for example, dupe is a word that's a symbol, right? But if you quote it, it will end up becoming just a parameter that's on the stack that we'll end up leveraging later on. The other case is an element that's part of fourth itself. That's an anti-fourth word called postpone. And I'll show you how we've defined it. I think I've actually defined it earlier, but if I did not, I will define it. Okay, I have not yet defined this. I will define this later on in my code. All right. What postpone does is and I'm just going to go ahead and read directly here. I'm quoting page 309 of the book. Postpone is always used to compile a word even if the word is immediate. So if there is a piece of code that's part of a word that's immediate and you want that code block, and you don't want to actually execute the value of whatever is available on the stack with the given word that's immediate, you can actually wrap that guy around a postpone, and it will actually go and just compile that code block itself. Um, so there are examples of this that we'll deal with later on when we're defining some additional functionality. But that just be aware of what postpone actually does. Its only job is to take immediate words and compile them as is, rather than evaluate them before compilation. So we saw some examples on how to implement some stuff, but we haven't actually talked about, well, what if, how do we end up leveraging this immediate mode, non-immediate mode sort of scenario that you were bringing up? So whether or not we're in compilation or in execution mode. So to do this, I'm going to first add a couple of more primitives, just because these are particularly useful that the book kind of mentioned when we're going to explain this concept. And they are create, name, and actually immediate. So what create does is it just makes a new fourth word, attaching it to the top of the dictionary, and sets the dictionary to being the top of that. What we do with name is if you have an anonymous fourth word that's on top of the dictionary, as you see right here especially, we want to be able to label that guy with something that's available in the top of the dictionary. And you could certainly do this. This is one way of actually defining, say a function. Immediate mode will then tell us whether or not we want to define that given word that's on the top of the dictionary to being what. So that's the head of the actual dictionary to being an immediate word or not. This way, if you define something that ends up you wanting to be executed all the time, and when you're in rather than compiling it, you can certainly do so. Now, some of this may not be necessary given that we're in Common Lisp, especially immediate mode, and we're writing our fourth in Common Lisp, but my understanding is this gives us some more functionality, some more control of dealing with the fourth interpreter at at the level of the actual machine. So this is particularly useful. This immediate mode stuff is particularly useful when you're trying to write a fourth inside of let's say a new ISA, a new architecture, writing an embedded system. So learning about it is particularly useful. So how do we actually use this? We'll deal with those other two that you just saw operations later on. So let's go ahead and add our two new operations. So we're now going to be able to create this. We added essentially create into our dictionary. We're going to define a compilation block now. So here, 276 and 277, what it did is it created a new fourth word in our dictionary. We haven't labeled it yet. There's no code yet related to it. But now we're going to define the code block of this guy. And let's say that this is just going to take... what this does is it takes us out of execution mode into compilation mode, and it compiles dupe and star. this is one way of defining, say, a square function. Now, we've defined square at this point, and but we haven't actually labeled it square. So if you try to use this at the top of the stack, you won't be able to actually look it up. So we need to actually attach a label to this. So now what we'll do is we will label this now called square. So if we go into our dictionary, let's see if there's a way I can do this. Yeah, let me see if I can do this. Pandoric macros. This is going to look a little ugly, but I don't know if there's any clean way of actually getting this guy out. Maybe I could do this. With Pandoric dictionary from new force. So let's see. So if you look at the top of this list right here, you will now see that the dictionary that that we have has at the top of the list a word called square. Its previous word is obviously going to be whatever was at the top of the dictionary before, which I think it was no-op, based on what I'm looking at here. We haven't set the immediate mode of this guy. All right, so it is a compiled word, and as you can see here in its thread, it itself is a set of closures of different operations, and these represent duplicate and star in that order. So if we go into here, for example, you can see that it's actually just a closure closed over values here. So how do we use this now? Because I think it's important to be able. So you can use it like any other word. So that dupe star that we saw in line 273, we've essentially compiled it. We've labeled it into its own function, and now we could just go ahead and use this like any other fourth word. We've now defined a way of creating functions inside our fourth interpreter, which is great. But it's a little clunky in terms of how we have to define it. First, we have to create the word on the stack. We have to go ahead and, define the body in a separate instruction, and then define whatever the name of it. There has to be probably a better way. Well, we're going to go ahead and create a couple of things. First, we're going to go ahead and add our create method into the standard library. And what this does is we're actually saying that we're taking create, and if you recall what Fort's standard lib add does is, let's go ahead and let's see here if I can do this. Yeah. So Fort standard lib add, what it does is it's converting a piece of code and it's trying to make it into a Lisp function that's going to then be added inside our standard library. In this case, what we're doing is and let me do this. This would probably be better. Fort standard lib. So let me just pull this guy down here. Okay. So what this is doing is Fort standard lib add is taking the body that we've just defined here, which is if we expand this, it's taking the standard lib add and concatenating the standard lib with create. And what is create doing? Create is taking us out of execution mode into compilation mode, saying that it wants to compile create, takes us back into execution mode, and then it defines that as being a left curly brace. This is going to come together when we start actually using this in code, because what this is essentially doing is it's giving us an easier notation for defining new functions. You could think of this as start defining and stop defining modes. That's kind of what the book is kind of leveraging, defining it. This left curly brace is what's often used in what the book calls fourth metaprogramming to improve this interface that this set of instructions that we saw earlier. What's particularly, and again, when we get into defining different things, we can actually you'll see how this will come together. The other thing that we need to also define is postpone. Now, postpone, I have to show you postpone in order for me to really post. Okay, so we've actually defined it here. Got it. All right. So let's go ahead and uncomment this, and then I can show you what this does. So what fourth standard lib add is doing here is it's using, let's see this. It's using create, because remember we defined create earlier, the left curly brace as being create. And we're defining something called postpone, which will then take us out of execution mode and into compilation mode. It allows us to define an immediate word as being compilable. This is the notation that will then be generated. It will generate a postpone, a open paren postpone right square bracket. Left square bracket, so that we get into this mode of actually defining what is our the ending of our code block. And all this code here, this postpone code, is associated now with this right curly brace, which we then associate with a particular name and the immediate mode of that given word. The way this all comes together is the following. With just this left curly brace and this right curly brace, what we now have is the ability to write functions in an easy-to-use syntax. And this is how you would do it in fourth. In actual fourth, you would, in this code here, use left curly brace, write the code that you want to associate with a given name, write the label of the name, and then you call name to actually associate square with this code block. So for folks who are seeing this, think of this as being equivalent to the following. This is equivalent. Actually, I'm going to do this. So let me compile that. So now our code, we don't have square anymore. This is equivalent to defun square x. Okay. The reason why we're writing it in reverse order is because, remember, we are using reverse Polish notation. Fourth expects you to write the operation that you're planning on defining at the very end. And name is basically associating this word, this code block with this, this label. So let's see what this does. If we do this, okay, we've now defined square again. And I could show that to you if I just do that and bring it up to the top. See, at the top of our stack is square, and then it's the code that it will normally associate it with. And if we run our code here that we did before, we have the ability now to run. It will go ahead and do what it was originally doing before, which is it will take 3, square it, and then print it out. It will essentially generate that duplication and the multiplication call for you. Now, one question for most is how is this different in fourth for in real fourth? So if you actually take real fourth code, how is our actual fourth interpreter slightly different? Well, in fourth, to create new words, they use a colon instead of a this create method that we created here. And I'm mentioning this briefly just so that for folks who wonder, well, if I ever want to write ANSI fourth or even standard fourth, how would I do this? I'm just going to briefly mention it, and the book kind of mentions it for this particular purpose. Lisp's use of colon, though, kind of contradicts. Lisp's use of colon is used for among many things, separating packages from their symbols that have been exported, which is a common use of using a colon. Is also used if you want to get unexported symbols, although that's kind of frowned upon if you end up using that kind of notation. So in order to prevent that kind of symbol conflict inside of our Lisp fork, we went ahead and defined one create, and then this left curly brace to start word definitions instead. So if you go into fourth and you wonder why left curly brace doesn't work, and I'm talking about a fourth that wasn't implemented in Lisp or following the example that the book provided, this is why. Additionally, there is, just like there's a right curly brace there, in fourth, they used a semicolon to determine the end of a code block, and obviously that contradicts, it conflicts with common Lisp's use of semicolon for comments. There is absolutely no reason for you to have this left curly brace, right curly brace stuff, but because of what we were looking at earlier, excuse me, I had something in my throat, which was, where is it? Here, which was in the way we're getting out of compilation mode and into compilation mode. There is absolutely no reason for you to create that left curly brace. But for folks who are used to this kind of code block kind of notation, seeing this, where we have to close it before we open it, just does not, first off, doesn't look right at all. This is what's called the normal bounds brackets problem. And you need to be aware that if you're writing it like this, you need to make sure that every time you see a right square bracket at the end, you should have at least a left square bracket. So since most people don't like aren't used to doing that because we like enclosing stuff rather than opening it up like this, it's more useful and more convenient to have a notation where we actually enclose some of our code, which is why that piece was introduced. So now we can actually use this guy for many other things. We can actually create a new, so this is just another example of us using square and printing it. We can use it to create other types of things like double. You know, you can define a dumb thing like double, which does this kind of the same structure, except it's adding instead of multiplying. And just like any other word, we can actually use them in conjunction with each other, which means they don't conflict with each other. We can actually go ahead and use this where we're squaring it after we doubled it. So that's 10 squared, which is 100, and then we go ahead and print it out. So we've seen how to define functions. We've seen how to what the difference is with immediate mode versus compilation mode, and we could even go well with dealing with rationals here too as well. So now I'm going to just go ahead and kind of give this example. New. This is a particularly interesting one. See that we can also handle rationals in our actual fourth interpreter that we wrote inside Lisp. So Lisp gives us a lot of this power for us for free. Additionally, we can actually do something a little nuts, and which is with this create word, we can actually associate it with non-symbols like primitives. This is something that I don't think is really necessary, but it's something that's there that we can actually do. The fourth, which is we could first define a label to a number, and then we can use the label to actually go and execute code. So you can use non-symbols, pass code. It's not just code to actually go associate. What's really, really odd is we can use any particularly Lisp object to name a given word, which means we could take, and this will really, really be screwed up, but you could do this. You can actually go ahead and the example in the book that it gave, which I was like, I don't know if this is actually a good thing, but okay. You can actually label a piece of code the following way, and you could then use it like this. And if you think that this is going to print a fixed num, you would be wrong. Okay, side question. Silly question. Love to know your Emacs theme. I'm using Doom Emacs, which creates this theme. It actually inherits the theme from Spacemacs that it forked off of and cleaned up. If folks are interested in a more interesting tutorial on do Emacs, I could come up with something and provide it here for the Common Lispers, so you guys can set it up for Common Lisp development. But put those into the comments inside the YouTube stream, and I will make sure that I'll put it on the list of things that we should talk about. So right now we've been playing around with our interpreter, but one thing to note about Forth that's very, very different from Lisp is Forth was defined, because Forth was defined for embedded systems development. I mean, that's kind of where it not only became popular, but that's where its roots were. And it was designed for small memory situations. There needed to be a way to access memory. So essentially doing pointer management and pointer scoping. Forth provides two particularly interesting operations for this. And one is the @ sign, which represents fetch, and the bang sign, which or exclamation point, which represents storing an operation. And we saw this earlier, but I didn't want to get to reviewing this until we got to this point. And the reason why this is necessary is, especially if we're porting Forth code into our Forth, we should be able to handle some of this notation. With Lisp, there's somewhat of a different context when we're trying to deal with pointers than actual Forth. Forth is actually getting proper memory addresses in a lot of cases when it's running, especially in an embedded system. But we need to be able to mimic that, so it's not so much that we are, accessing memory, but we're accessing in a way that's consistent with our Lisp environment. Does that make sense for folks? So I think that's a particularly important notion to be aware of, and that is we are defining memory retrieval and memory storage within the context of Lisp. So although you're going to see exclamation point and @ sign in these examples, what they mean might be very different than how they're going to ultimately be used if you end up using a real Forth interpreter. I'm putting that context in just mainly because of the fact that since we are in Lisp, this is not, and we're trying to implement this semantics, this does not mean that we're actually implementing a way for you to access memory directly in any sort of, machine environment. We're just dealing with consoles. So with that context in mind, what does fetch then and store mean? Well, fetching something from memory very well could be just simply pushing whatever is at the top of the stack, the car of that console, back into the top of the parameter stack. So if you gave me a memory address or a console that you wanted me to get a particular option from, I'll just take your console, go ahead and car it, and then return whatever it is back onto the parameter stack. Now, storing then would be something different. So storing means we're taking the value that's at the top of the stack, and that is some console that we're actually storing into, and we're then grabbing whatever is the next value that's at the top of the stack and storing it in the car of this console. All right. So if you think about how this might roll out, if your stack is, let me see what's the best way of actually illustrating this. Just check something here. I don't need to specify anything in here, right? No, I have to specify. That's right. Never mind. That is a dumb thing that I just did. Cons 1, 3, 2. It is a dotted pair. So can I do cons? No. Yeah, I think I might need to do something like that. Cons nil though, I don't think I can do, right? Yeah. Okay. So I can use cons nil to make what I would consider to be an empty cell. So if you end up, so in fourth, this would be, yeah, that's one way of doing it. So if we do, the following, we let me first compile these two, and then I will show you guys in a new interpreter. Let's create a new interpreter. New fourth interpreter. Okay. So now we have a new interpreter. Go forth, new fourth. And what we could do is what we saw earlier. We will take a value 1, okay? We will then take our empty value. We will go ahead and store what's in. We'll store 1 into that memory location, because again, that's just a simple console, and then we'll just go ahead and print it. Now, let's see what happens. It did not do it as I thought it would. Let's see what this does. Okay, so we actually have to pop the location onto the stack and then card the location. So let's see what happens when I do this and look at the parameter stack. Pandoric macros with Pandoric. Oops, sorry, not dictionary. P stack. There's nothing else on the P stack. Okay, let's do this. Doop, doop. Control stack. Okay, give me a second. I'm going to go and create a new one. Oh, wow. That looks wrong. I must have messed something up here. Let's see here. Okay, I see what the problem is. It's because I am trying to do an infinite list here rather than this. So don't use dupe dupe in the same area next to a stored cell if you're trying to store it, because that's essentially a way of creating a potentially an infinite list, and without the appropriate um, global turned on. I think it's called print circle. Um, that's not going to work. I will show you that in a minute, because you could also use this to create cyclic lists too. That's the example that's in the book. Let's go and look though at our parameter stack. So if you look at our parameter stack, this is what is actually in the parameter stack. It's a list of 1. And the reason why earlier you were not getting sorry. The reason why when we evaluate you're getting 1 is a cons pair where the cater is nil is treated as a single value inside common Lisp, and it returns it that way. It doesn't return you the open paren unless you specify it. It's a little weird that that's there. I would have expected it to do this, but for some reason it didn't do that. This is what I was kind of expecting, but for some reason the output of this is providing the top of the stack. I'm guessing that it's evaluating that before it actually returns it. That's beside the point. Our parameter stack is actually correctly defined as being as a cons pair of 1 with nil, which means we're actually storing the operation. What we could do here now is once we store it, we could, we can at any point in time retrieve the value, and so we'll do, let's see, how would we do that? We just simply use at here, it'll just go ahead and do what we're expecting to do, which is retrieving the value and then pushing it back onto the stack. Is not of type list. What are you talking about? Would have expected the top of the stack to be... Oh, never mind. That is wrong. What that's doing is that is a single list, not a list of lists, I just noticed. So what we're expecting is this, and instead what we got was this, which is wrong. So we need to go and debug that. See this. One call nil. Okay. Best way to actually probably do this is go into fourth handled So what I'm doing is I'm writing a couple of debug statements in here, just so that I'll be able to figure out what's ultimately being called. We don't have any for it in there. And then if compile in, otherwise we push it in. And don't worry, I'll correct the formatting here in a minute. This guy is going to be, what is the right thing? It will be, okay. Go ahead and recompile that guy, which means we need to go and recompile our interpreter, which for some reason does not like the fact that I tried to do this in real time. I'm going to reload here. To create not found. Let's see this. Whoops. Ah, dang it. Did it just freaking... My apologies, for some reason I did the wrong thing. Yeah. Weird. Why is that happening? This is what I was looking at earlier. For some reason, when you load all the values, it is not recognizing got it. Weird. That should have worked. Server side close. Slide. My apologies. A few technical difficulties today. Do this. For some reason, it doesn't like when you when you're compiling the code, it does not seem to enjoy having all these examples available. Might be because of the fact that I haven't exported any of these symbols, which is very, very likely, but that would be a bit surprising if that's the case. Folks who know better watching the stream, please let me know. Let's go ahead and uncomment this. I'll try and figure out why that weirdness is happening. That shouldn't be happening. Go ahead and add these guys to our standard library section. Doing just a little bit of cleanup before we continue here. There we go. That's the reason why. Okay. So let's go back to what we were looking at earlier, which is this guy. And coded value found. So it is going into non. So what is it doing there? Let's see what happens when I do this. Okay. Okay, I think I see what the problem is. I don't think I need to do this. This now should be. This is not actually storing the way I expect it to. Okay. So let's go into the @ sign here. I'm going to have here. I'm going to return what the value is here. That's odd. I've never seen that happen. Shift. Let's look at this. I have to. Maybe I'm calling it wrong. Should be calling it wrong. It doesn't look right. Let's see here. One of the nice things of coding this interpreter in straight Lisp is you could write some of these debug statements directly while you're interacting with the interpreter. Not even calling the see. Let's see. Not immediate. Let's go back up to this. Created not found. Create should be available. Let me see what create is. Sorry about that. Okay. Let's see here. Where would that be causing an issue? Folks wondering that what I'm trying to do is there's this one issue related to the storage and retrieval that I'm trying to clean up. That I'm before we uh, continue, just taking a little bit of a second, trying to. There we go. And yet it did not return the value that it provided. Why not? Let me do this again. Let's do this as two separate operations. We have nil, we have 1. So now, let's do go for it. Store 1 into nil. See? We just popped it without actually. So there's a problem with our setting here. Let's do this. So the example in the book kind of gave this original, and you could find this code, this fourth interpreter available. So in the Let Over Lambda website, I'm trying to kind of reconstruct it and go through it bit by bit. But if you want to follow along, you can certainly do that too as well. Current value. Okay. So we do current value. And so I'm kind of expecting that current value to be set to 1, and then the location is just going to be the empty list with the nil that we set earlier. Okay. So we might need to restart our interpreter here. Just one more time. Okay. And I'll figure out a way of making it so that I can actually have this compiled code available when we start the script. I haven't yet to clean that piece up yet. So this way you guys don't need to constantly do what I'm doing, which is restarting the Lisp buffer. There seems to be an issue with the why it doesn't like the macros being available there the way it is. Oops. Okay, we have that. So it's getting the right values. Got it. I think I know what the problem is. I think I have to, we're not pushing this back onto the parameter stack. That's basically what it is. We're storing it at the location, but we're not pushing its return value onto the parameter stack. Okay. Yeah. This. Push location p stack. I don't know if this will work, but we'll see. No, it didn't compile it. Okay, got it. So I'm going to have to regenerate everything. Oops. No. Okay. All right, this should do it. Now if we go and look at the parameter stack, and that's what we're looking for. So lesson, please, 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 when you're defining, this is a mistake in the book. I didn't even realize it until I just looked at it. It does not store the, so for folks following along, and I looked at the original source code on this on Let Over Lambda 2 as well. The storage operation is not actually, it's popping off the location that was put into the parameter stack. It applies the operation, but it actually doesn't actually push the results back onto the parameter stack, which is actually incorrect. You always have to push the return value back unless you do an explicit drop. So that's why we were having this issue earlier. I was wondering why that was getting kind of messed up, so I got that working. But yeah, this by itself has its stands. Now we have memory retrieval, we have memory storage, we have the retrieval you can actually see here simply by doing this, which is what's it? I think we just make sure that the retrieval actually works too. Right. So we do we just need to call the @ sign here, and this should now work actually if we do 1. So let's go ahead and store and retrieve it. Although, so we're going to create a new interpreter, and we check. What we did was we stored it, we popped off the memory location, retrieved it, and pushed it back onto the stack. So now, what we could also do is do this, just to show you the beauty of this fourth interpreter. We're going to duplicate the memory location, and then we're going to grab the value from that memory location. Then, so it's going to create a new console from what's already on the parameter stack, and then it'll retrieve the value from that one. So now, if we go and look at the parameter stack, you see at the top, like I said, it took the. So let's go through this. We pushed 1 on the parameter stack. We pushed a memory location on a parameter stack in the form of a console, okay, with an empty value. We stored 1 into that console. We duplicated it, which means it created a new console with 1 in it. And then we went ahead and retrieved the value from that console. So now this is what our parameter stack looks like. So if we go ahead and then, decide to call print on here, it's just going to go ahead and print that value. Okay. There's a lot of other things to go into here to make fourth metaprogramming even further that we need to define. And this is going to include the definition of another thing, which is kind of integrating our fourth interpreter into the into our Lisp itself, and that is fourth. I'll just briefly touch fourth unary definer, and then we can cover binary definer next week. But I thought it would be fun to at least get unary definer defined, because it's pretty useful. So what do I mean by fourth unary word definer? Now, this is very specific to Common Lisp, although I think other languages that if you're going to develop this in, or you're curious in developing it, you might do something similar. Common Lisp has a bunch of functions that we may want to have as part of our standard library. Okay, that's just so that it's convenient for us to actually go in and define these. If you don't mind, I'm going to go ahead and comment this stuff out so that this doesn't affect our ability to potentially reload stuff until I get the go for it stuff kind of fixed. Let me just do this, which is for now. I'm just going to go ahead and comment this guy out. And what I'm going to do is right underneath here, we're going to go ahead and define our Unary definer stuff. Okay. Print this up here. Move that up. Okay. So let's talk about Unary definer, Unary word definer. Okay. This is another macro. Okay. That's going to take Unary word definer. This guy is going to take a list of symbols, essentially. Okay. Okay. And I'm talking about Lisp symbols that are defining functions. Okay. And we're going to label them as words. What it does is it's going to go ahead and map car through this. Again, we're going to use a prog in here because we're going to have multiple statements, although and what we're first doing is we're remember we're doing an array splice here. We're generating a piece of code. We're map carring on the following lambda, which is going to define, again, we're using anaphoric macros here, so it's particularly useful to actually be able to stick this guy into so recall, this is our hash sharp reader is a reader macro that goes ahead and grabs whatever is in its internal environment and then sticks it into the actual structure of the code that we're actually generating. In order for us to do this, because we're using a read table, we're going to have to use an eval when. So I'm going to go ahead and wrap this guy. And for folks who are looking into this, who have a question regarding, well, wouldn't it be better to group a bunch of eval whens into the same? I don't know what would be the best practice. I'm just kind of whenever I'm defining a particular section, I end up doing an eval when it needs to have the reader macros leveraged. Otherwise, I don't do it. So we do an eval when, load top level, execute. Okay. And what this guy is doing here in this hash sharp quote that we've defined in hash back quote we defined in previous episodes, we're going to go ahead and define a fourth primitive. Okay, this is our defining of a word inside of our fourth dictionary. We're going to use our A1 variable that we've defined already in the generation of that sharp backquote. And we're unquoting it. And if you're wondering what that nil is, that's the general fourth structure. It's if you look at fourth primitive here, um, this is going to behind the scenes generate a dictionary value, and we can look at it right here. It creates a, which in turn generates a list that will take the code and then correct it so that it appropriately links up into our primitive forms. Global variable. And then once we have this defined like this, we just go ahead and structure it to use whatever we've added, which is simply pushing our unquoted variable onto the top of, oops, my apologies, I'm messing this up. We're pushing the value in the top of the p stack, so the result of this onto the p stack. And the reason why we're doing that is recall, this is a unary operation that we're actually going and I'm grabbing from Lisp. And unary operations take a single argument. So this effectively is just pushing the code block of whatever unary operation top of the stack onto the top of the parameter stack itself. So it's in effect evaluating that code once it gets popped off. And then that generates, the thread that the fourth primitive word will end up using. And what we're doing here is, in this map car, we're mapping this sharp code on our words. Okay. And where we're actually going to end up leveraging this is inside defining particularly lists like we did right here. We can call this guy directly. But before we do that, let's go ahead and try something out here. Let's go ahead and do a macro expand on the following code, which is calling fourth unary definer on the most known fourth unary definer, which I forgot to compile. Right, because the sharp code is not in there. Changed it back. Let's do this. Make this guy in here. The reader macros is a read table that I previously defined in a different file, which I'm pretty sure I've checked in, but we'll see. Still says it can't actually find it, which is odd. Yeah, this is weird. Let me do this. I don't need this then. This is why I've been having to restart my Lisp, for some reason, using the different read tables work well when you're loading up the stuff into your image, but if you don't actually for some reason I've been having some trouble actually using different read tables when I'm trying to compile code in real time in my Lisp image. So read tables in general is kind of wonky, but I'm still learning how named read tables kind of work. So folks who are familiar with named read tables, please let me know if I'm doing something incorrect or some good practices or suggestions. Let's go here, load this guy up. Hopefully this doesn't throw up an error again. Okay, good. Set up package. Okay, go here, and let's go ahead and macro expand fourth unary word definer not. My apologies. Let me do this. So what that code does is it goes ahead and generates, multiple this fourth primitive definition. Now you may be wondering, well, this has a prog end. Why do we need it? Why do we need that here? Well, for this particular example, since we're only defining not, it doesn't seem necessary. But let's say that we want to do car, kidder, so forth. This will generate all these fourth primitives for us. So what we'll do is we're going to use this to go ahead and define a bunch of our Lisp primitives that we're kind of used to having available to us to being part of our fourth dictionary. So now what we'll do is and I'll leave this here, which is we're going to go ahead and use fourth unary word definer to grab all of a bunch of common Lisp operations, unary operations, useful for programming as well. And this will include things like some of our standard not, car, kidder, cater, and the standard variables going up to the things. At least we're going to mention odd and even. Sorry, we're going to use at least up to three levels of depths. Car, kidder. And if you want, also we'll add, Kadar and odd and even. So now that we have these, we've effectively added them into our dictionary. We can actually go ahead and use them. So these are now part of our Lisp interpreter. Let me go ahead and do this. Order the value. This. Oops. Okay. And let me just do one more restart here, and I will give you a quick demo. So let's go ahead and set our new fourth interpreter here. That, and let's do go forth, new fourth. Let's add a list to, and let's grab the cargo list. Now if we go and look into our P stack, you'll see that it took the list, pushed it onto the stack, grabbed the car, and pushed it back into our P stack. Nothing spectacular there, but as you can see now, what we've done though is pretty powerful. We've taken fourth, we've defined a fourth interpreter, and using fourth, we are adding to fourth what's already available in Common Lisp as part of fourth, and as part of the fourth dictionary that we've implemented. And we've generated that code very, very quickly without anything more than a simple macro to go and define that template. And because we have that access to the compiler to actually go in and generate these things, it's all first-class citizens. So that means we did not actually have to go and modify the compiler to actually go in and introduce this piece of functionality. I'm going to end it here, given the fact that we've now gone a little bit over 2 hours. I do appreciate all you guys staying on until we got this through. Next week, we're going to continue on this. We're going to add the binary word definer, and then hopefully from there we could do some pretty interesting stuff with branching and adding more stuff where we can actually start looking what ultimately could be a Lisp on top of fourth too as well, which is kind of what the author tries to get to. And in the meantime, we'll also cover what the D-table abstract register is, as well as some other things that we have, odds and ends that we have not completed yet. So I, again, appreciate for those staying on for these 2 hours watching this. I hope it was insightful. If you guys have questions and comments, go ahead and post it on YouTube. I will post this corrected code on top of GitHub. Those following along, the original source code is available on letoverlambda.com for you guys to take a look at it. There were a couple of corrections that we've been introducing as we've been going along with what was available. You could think of it kind of like a running errata, just by going through what's in the book. I think the next week we're gonna hopefully between next week or the following week we'll be finishing off this, and then I'll lead to more announcements regarding what's going on in future episodes. Before I let you guys all go, the Atlanta Functional Programming Meetup is looking for speakers for talks. We're trying to set up our virtual speaker schedule. Please contact me or Judd Taylor Dagmar on Functional Programming Slack. Has me as well. I'm available as Bugram both on Functional Programming Slack as well as the Lisp Discord server if you'd like to speak and give a topic. Other than that, I'll see you guys next week, and thanks for joining me.